Welcome to this virtual lecture course on electromagnetism. I'm Dr. Andrew Mitchell, and in this lecture I'll be talking about magnetostatics. That's the behaviour of static magnetic fields due to steady or time-independent currents. In the last lecture, we took as our starting point the Biot-Savart law, which tells us about how magnetic fields are generated from currents in wires. This can be taken as an experimental or observational fact about nature. We generalised this to a 3D current density, and from it derived Ampere's law in integral form, which is basically the magnetic analogue of Gauss's law in electrostatics. We also derived Maxwell's equations for magnetostatics, which are of course in differential form. In this lecture, I want to do a couple of examples of applying Ampere's law, and then I want to tell you about a reformulation of magnetostatics in terms of the vector potential. We'll see that this is a powerful new formulation which exploits some of the information contained in Maxwell's equations. And we'll also see that its power comes in part from the invariance of physical observables to gauge transformations of the vector potential, which allows us to simplify some of the equations, and I'll tell you all about that. Finally, I want to discuss the multipole expansion of the vector potential, which is a clever and elegant way of organising the information contained in the vector potential as a power series in the inverse separation between the source and field points, and allows us to make rigorous and controlled approximations for arbitrary, complex field configurations. It'll allow us to see that there is no monopole term, and also see the structure of the magnetic dipole term. Okay, let's get down to work. In the last lecture, we derived Ampere's law in integral form, and here it is. On the left-hand side, we have a line integral of the magnetic field around some closed loop, which we call an Amperian loop. On the right-hand side, we equate this to the total amount of current passing through that loop. So let's do an example, probably the most basic and important example. A current passing through a 1D wire. So pictorially, we have some kind of wire in 1D. We have a current flowing through it, which we call I. And what we want to do is to work out the magnetic field that's due to the current flowing through this wire. And we can do this using Ampere's law. How do we do that? Well, we have an integral, a line integral on the left-hand side, and what we actually want is the magnetic field, which is inside the integral. So we have to be a little bit clever in the construction of our Amperian loop. The way we do this is to construct a loop that has the right symmetry properties. So, for example, I construct a line integral loop like so. It's a circular loop that's centered on the wire. And we imagine that this loop has a radius s in cylindrical coordinates. Okay, so how can we use the Ampere law to extract the magnetic field? Well, we have the line integral of B, the magnetic field, around this Amperian loop. But the choice of our loop helps us in two ways. Firstly, the magnetic field is at all points parallel to the path that we take. Why? Because we know from Ampere's law, and we know from the Biot-Savart law, that the magnetic field curls according to the right-hand rule around the wire. So if we have a circular loop centered on the wire, then at every point the magnetic field is going to be parallel to the path that we take. And this allows us to get rid of the vectors in this equation. We can just have the magnitude of the magnetic field integrated along the path, because B dot dl has no vector component. So B is at all points parallel to the path taken dl. Okay, we're not there yet. We need to further extract the magnetic field from inside the integral. And again, we can actually do that because of the high symmetry of this situation. How come I can take the magnetic field outside of the integral? Because the magnetic field is constant along the line of integration. Why is that? Again, it's because of the symmetry of the problem. The magnetic field can only depend on the distance away from the wire by the cylindrical symmetry of the problem. And given that we have a constant radius around our circular loop, then the magnetic field will be constant along the loop. So the fact that the magnitude of the magnetic field only depends on the radial distance from the 1D wire by cylindrical symmetry means that it's constant for a circular loop. And then we're just left with the line integral around a circle, and we all know how to do that one. It's 2 pi s for the circumference of the circle times b. And we know that this thing is equal to the current enclosed by the loop, and we just have one wire passing through the loop with current I, and so the total current passing through the loop is just I. So now, finally putting this together, we can find that the magnetic field is mu naught I over 2 pi s, which is actually what we got using directly the Biot-Savart law in the last lecture. This is just the magnitude. To find the direction, we have to use the Biot-Savart law, and we'll see that it would be a circumferential direction in the phi hat direction. Okay, another example, an important example, is the magnetic field due to a solenoid. A solenoid is basically the magnetic equivalent of a capacitor in electrostatics. And we basically have, in pictures, a setup that looks a bit like this. We have some kind of cylinder, and then we have a wire loop that wraps around our cylinder with many loops of this wire. And a current is made to flow in this wire. We'll say that this current is a current I. For the sake of completeness, let's also say that the radius of this cylinder here is capital R, and we'll say that the length of this cylinder is L. So what we have is, if you like, n closely wound turns of wire per unit length. So this is how we're going to quantify the density, if you like, of these loops. So we have n closely wound loops of wire per unit length. And this is basically equivalent to a uniform surface current. This is a bit of an approximation, of course, because actually we have 1D wires, but we're imagining that they're so tightly packed, they're so dense, that basically we have a continuous flow of charge around this thing. So what we're now going to assume is that the length of this cylinder is much, much greater than the radius, and we'll ignore, therefore, edge effects. If we didn't do this, then we would have some eddy currents and some complex, or complicated, I should say, magnetic fields towards the edge of the solenoid, but we're not interested in those right now. So we're going to ignore those edge effects. We're also going to ignore the tiny contribution of the magnetic field coming from the longitudinal current. So as you can see, when the current comes in at the bottom and comes out at the top, it's obviously travelled a vertical distance L, but we'll actually ignore that and we'll just consider the current circulating around. So there will be some small contribution to the magnetic field due to the fact that the current travels upwards a bit. But if you think about the number of times that it'll spiral around this thing, then that's much, much greater than the distance travelled in the vertical direction. So we're going to ignore the effect of the longitudinal current. And therefore, we just model the wire turns in the solenoid as circular current loops. Rather than a spiral, we think of them as just densely packed circular current loops. Okay, what is the direction of the magnetic field? So we have cylindrical coordinates. They would be the sensible thing to use in this case. So we'll define a point in space R according to the radial extent S, the angle phi, and the vertical position Z. So they're our cylindrical coordinates, which we're going to use for this. So clearly, in this problem, there is no radial component of the magnetic field. Why is that? Well, from the Biot-Savart law, we know that if we were to change the direction of the current, then the magnetic field would have to change, because the magnetic field is proportional to the current according to the Biot-Savart law. So if we change I to minus I, we would expect B to go to minus B. However, this would happen by turning the solenoid upside down. If we turn the solenoid upside down, it's like we're reversing the direction of the current. But this cannot change the magnetic field from being in-pointing to out-pointing just by turning the solenoid upside down. So this tells us that the radial component of the magnetic field must be equal to 0. So that's a symmetry argument. So the radial component of the magnetic field must be equal to 0. There's also no circumferential component. Why is that? Because an Amperian loop, which is coaxial with the solenoid, would have no current passing through it. So remember that we decided to ignore the effects of the longitudinal current. If we imagine a coaxial, let's just draw it. Imagine that we have a coaxial Amperian loop. Here's our solenoid, and then we have an Amperian loop which passes like this. There's no net current passing through this thing, or at least it's negligibly small. And so that would mean that there is no magnetic field according to Ampere's law. So there's no circumferential component either. Okay, so what we're left with, therefore, is that the magnetic field, if it's non-zero, which we'll find that it is, if the magnetic field must be pointing along the longitudinal direction, the z direction. So the magnetic field at some point r in space is actually just the z component and it's in the z direction. So the field must be parallel to the solenoid axis. Due to the cylindrical symmetry, there is no phi or z dependence. So it just depends on z. Okay, so how can we actually work out what this Bz of R is, the actual magnitude of the magnetic field? Well, we're going to use Ampere's law. Let's just sketch the system again. We have something like this. Let's consider making an Amperian loop outside of the solenoid entirely. Let's have a little box like this. Let's say that this box is of vertical distance L0, and let's imagine that we have an inner radius A and an outer radius B. So we've got a little box here. The current enclosed is 0. And so, if we use Ampere's law, we're considering the line integral of the magnetic field around this loop. What does it look like? Well, we have Bz. We argued that that's the only contribution that we get for a radius S equals A. And we integrate over the length of the line, that's L0, minus Bz at S equals B, integrated over the length of the line, L0. The horizontal bits of the box don't contribute because we only have a magnetic field in the z direction. And by Ampere's law, we equate these two things, so this thing must be equal to 0, and therefore we know that the magnetic field at A is equal to the magnetic field at B. And this argument applies anywhere outside the solenoid. So what we have is the general result that Bs is equal to Bs primed for any S and S primes greater than the radius of our solenoid. There's one other thing we know, which is that because we have a localized current density, the magnetic field must go to 0 when we're infinitely far away. If we're infinitely far away, the fact that we have a current density somewhere else is unimportant. The magnetic field will be 0 at infinitely far away. So if we send the radius off to infinity, the magnetic field must go to 0. And if the magnetic field is 0 out at infinity, it must be 0 everywhere outside. So we have the important and somewhat counterintuitive result that the magnetic field is actually 0, strictly 0, when we're outside of the solenoid. Okay, what about inside the solenoid? How can we understand what's going on there? Well, let's make our sketch. Here's our cylinder, and we have our wire loop. What we can do is consider Ampere's law again, but now consider a square loop that's half inside the solenoid and half outside of the solenoid. Again, let's say that we have a vertical distance L0, and let's say the inner radius here is S. Okay, so again, we use Ampere's law. This S is less than R. So we consider the line integral of the magnetic field. We know by symmetry arguments that this is just the Z component of the magnetic field, which only depends on the radial distance times L0. The horizontal parts of the loop don't count because there's no radial component of the magnetic field. And then we're integrating outside of the solenoid, but we've just worked out that the field outside is equal to 0. So that's all we have. And this thing is equal to the current enclosed by the loop. And this is not 0 in this particular case, because we have some wire loops that are passing through this thing. How many? It's n loops, and each of them is carrying a current I. So that's the total current n times I that passes through this thing. And it's n loops per unit length, actually, so we need to multiply this by the L0, the length. Okay, so we actually have something non-trivial here. We've worked out that the magnetic field is mu naught n I in the z direction. And this is when we're talking about radiuses that are, oops, that's not correct. When we're talking about radiuses that are smaller than the radius of the solenoid itself. The magnetic field is 0 when we're outside. And so we see something rather interesting from this analysis, which is the magnetic field is strong, it's homogeneous, it just points along the z direction, it's uniform everywhere inside the solenoid and 0 outside. So this is kind of like why I said that this is the magnetic analogue of the capacitor. In the capacitor, we have the situation where we have 0 electric field outside and a strong homogeneous electric field between the plates. So the solenoid is like the magnetic version of the capacitor. So we have magnetic field lines that sort of come like this. Okay, let's look at another example of using Ampere's law. Which is the case of a capacitor which is actually moving along. If we have something that is charged and it's moving, that constitutes a current, and then we'd expect there to be a magnetic field, and we can use Ampere's law. So in this example, let's have a look at a moving capacitor. In particular, let's ask ourselves the following question: what are the electric and magnetic forces on the plates? So previously we've looked at the electric forces, now let's also look at the magnetic forces. Okay. So how are we going to answer this question? Well, first of all, any good question, answering any question basically starts with drawing a small cartoon so that we can orientate ourselves to understanding what's going on. Let's define everything. So let's say that there's a charge density plus sigma on the upper plate and a charge density of minus sigma on the lower plate. And we'll imagine that this whole system, both plates, is moving along the x-axis with some velocity v. So let's first of all, in the first part of the question, work out the electric forces on the lower plate. Now, we don't need to separately work out the electric forces on the upper plate because we know Newton's third law, and we know, therefore, that the forces will be equal and opposite. So how do we work out the electric forces? Well, first of all, we need to work out the electric field, and then we can use the Lorentz Force law. How do we work out the electric field? We use Gauss's law. This tells us that the field flux through some area is equal to the charge enclosed. Let's say, just for the sake of concreteness, that the up vertical direction is going to be our positive z direction. Okay, so the electric fields due to the upper plate is, as usual, going to be the area that we're considering times the electric field and then the charge enclosed is the area times the charge density. This is the usual application of Gauss's law. Where did I get that from? Well, we consider the upper plate, we consider a Gaussian surface, which is like a little box that sticks up and below the plane of area A. The field flux that goes through this, the electric field flux that goes through this little box is going to be E times A for both of the surfaces, the upper and lower surface. That's why I get a factor of 2. Good. Okay, so what we learn from this is that the electric field, we can reinstate the vectors. Is minus sigma over 2 epsilon naught z hat at the lower plate. Why minus? Because we're looking underneath the top plate, and therefore, as you see from the figure, the electric field lines are going down, and that's in the negative z direction. Okay, so if we want to know what the electric force is on the lower plate, this is F elec, I'll call it. This is the charge times the electric field. What is the charge? Well, this time it's minus sigma times A times the electric field, which is plus overall sigma squared A over 2 epsilon naught z hat. So what we're really interested in, I guess, is the force per unit area. Let's call that little f. That's just plus sigma squared over 2 epsilon naught in the z hat direction. It points upwards. Plus means upwards according to our signing convention. And of course that's correct. If we have a negatively charged lower plate, it will be attracted to the positively charged upper plate, and that force is upwards. Okay, so that's just a recap reminder of what's going on the electric side. So now let's consider what's going on the magnetic side. What are the magnetic forces on the lower plate due to the upper plate? So how do we do this? Well, we're obviously going to use the Biot-Savart law or Ampere's law. Let's make, again, a sketch of the upper plate. This is the one with the positive charge density, plus sigma. And remember that this thing is moving along the x-axis to the right with a velocity v. So presumably there's some kind of magnetic field generated. In which direction does it point? First of all, why is there a magnetic field? Well, we have a charged plane and it's moving, so that constitutes a 2D current density, and we know from the Biot-Savart law that that should generate a magnetic field. So let's look at the Biot-Savart law first to argue the direction of the magnetic field. So this magnetic field is generated because there's basically a surface current. Why is it a surface current? Because it's a 2D charged plane that's moving. So we use the Biot-Savart law for a surface current, which looks like this, as derived in the previous lecture. And we have a surface current which is basically just the charge density sigma times the velocity v. Okay, so can we use this to argue what's happening with the magnetic field? Well, the magnetic field B must point perpendicular to K, the current density. That's because in the integral there, B is equal to K cross the script R, the separation vector between the field point and the source point. So this tells us, looking at the Biot-Savart law, that B points perpendicular to K because K appears on the right-hand side through the cross product. So we know that whatever's on the left-hand side is going to be mutually perpendicular to both K and script R. And there's a translational symmetry in the plane, which means there can be no Z component. And that's pretty important. Also, finally, we can use the right-hand rule when looking at the cross products there in the Biot-Savart law. And what we see is that the magnetic field must be out of the page when we're above and into the page when we're below. So we use the right-hand rule when we see a cross product as appears on the right-hand side of the Biot-Savart law. The right-hand rule tells us that B is out of page when we're above and into the page when we're below. Okay, so let's just draw it on our sketch. When we're above, we have something that's out of the page, and when we're below, we have something that's into the page. It's got to be perpendicular to the plane and the velocity. So there we have it. Okay, good. So now let's switch and use the Ampere law to actually work out the magnitude of B. How do we do that? Well, let's use an Amperian loop that's using the same logic as before will give us, so the magnetic field should be
parallel to the path taken along the loop, and it should also be constant along the loop everywhere. So let's imagine that we take this little path here. The vertical components are not going to contribute, and the horizontal components are actually parallel with the magnetic field, and also it's constant because the only dependence of the that the magnetic field can have must be depending on the distance from the plate. So we use Ampere's law. We have the closed loop line integral B dot dl, and this is going to equal the current enclosed. Okay, very good. What about the left-hand side? Well, we can do this integral. It's just going to be 2 times b times L. Let's say that the length of this loop edge here is L. Okay, so that's 2bl, 2 just because there's a contribution from the upper side of the loop and from the lower side. Because the loop is going round in a particular sense, the contributions add up rather than subtract. And then on the right hand side, the current enclosed is just sigma times V times L. And then we have to multiply that by mu naught. Okay, so that's it. So what we can find is the magnetic field is very simply equal to something that involves the velocity and the charge density, as you might expect. And that's, of course, quite a nice result. Okay, so what about the actual force? We wanted to know the force rather than just the magnetic field. Again, we'll look at the force per unit area. That's going to be F mag, I'll call it, lowercase f for force per unit area. How do we do that? Well, we have to use the Lorentz Force law for a 2D current density. Force per unit area is going to be 1 over the area integral K cross B is the force due to a 2D charge density, a 2D current density as we saw before, integrated over some area. So you can see that this integral of this thing over some area divided by the area is like the average, if you like, and that's what we want, the force per unit area. And so that whole thing is just going to be K cross B, because both the current and the magnetic field are constant over any particular area. You can also think of shrinking that area down to 0, making it sort of a differential, if you like. So we have to use, again, the right-hand rule to work out what direction, because we have a cross product of K cross B, and what we find is that the force is downwards. What's the magnitude? Well, if we're careful with the signs, we find that it's minus mu naught sigma squared V over 2. Okay, so this is an interesting result, so let's maybe just take a little minute to have a little think about this. So what we see is the magnetic force and the electric forces are actually in opposite directions. So an interesting question would be, if they're in opposite directions, when would they cancel? Maybe you could imagine moving this capacitor quite quickly so that the magnetic force grows. You see that there it's proportional to the velocity. Sorry, it's proportional to the velocity squared. is proportional to the velocity squared, so that as I move faster and faster, the magnetic force will grow. Is it possible that this can actually cancel out the electric forces, which you'd ordinarily imagine would be dominant because we have two charged plates in close proximity? When do they cancel? So what I mean is, when does the magnetic part of the force equal minus the electric part of the force, so that the net force is equal to 0? Well, we can just do a quick back-of-the-envelope calculation. And what we find is that the velocity squared has to be, for this to happen, 1 over mu naught epsilon naught. And as we know, this is actually the speed of light squared. So what we see is that only when the capacitor is moving at the speed of light would the electric and magnetic forces cancel. Now, normally we expect the electric field to be much stronger than the magnetic field because epsilon naught is much, much greater than mu naught. Epsilon naught controls the strength of the electric field, mu naught controls the strength of the magnetic field. And just because of the sizes of these fundamental constants, we know that the electric field is usually much, much stronger. In this particular case, because the magnetic force is proportional to the velocity squared, we can enhance that by just moving more quickly. But it turns out that the magnetic force cannot be bigger than the electric force, however fast we go, because of this relativistic speed limit of v equals c. And it's only actually at this limiting case, where the velocity of the capacitor is equal to the speed of light, that actually the two forces are equal in magnitude and opposite in sign. So this actually begs a more general question, which is rather interesting, which is, how come we can actually observe magnetic phenomena at all? Surely this is a relativistic effect, and we see that the large electric forces, basically at any moderate speeds, always overpower the magnetic forces. They're only comparable in magnitude when we really are in this relativistic limit, v goes to c. So how come it is that we actually observe magnetic phenomena at normal velocities? And the interesting thing about it is that usually, if we consider like a wire or something like this, we can have a net charge which is equal to 0. So we actually have huge electric forces between the positive and negative charges, but they just cancel out. So what we can have is a situation with a current flowing in a wire where you have a net charge is equal to 0 at any bits in the wire, but you still have a flow of charge, a steady current, and this produces a magnetic field. So it is possible to observe these magnetic fields even at moderate speeds, just by this very delicate and fine cancellation of the electric forces due to positive and negative charges. Okay, so the second topic in today's lecture is to do with the vector potential in magnetostatics. So before we actually begin talking about the vector potential, let's recall the situation in electrostatics. We have a potential there as well. Remember that the way we derived the electric potential was through the following argument. We had Maxwell's equation for electrostatics, which tells us that the curl of the electric field is equal to 0. And this is a very important equation because it constrains the type of vector field that electric fields can be. So not any old vector field can be an electric field, only vector fields which have no curl or are irrotational can be electric fields. And this equation that I've written down here is basically a constraint equation, but note that it's a vector equation. So I'm trying to be precise here by writing the vector arrow on the 0 on the right-hand side, because this is actually 3 equations. And they constrain the form of the electric field, so let's call them 3 scalar constraint equations. And they determine the kind of fields that can be electric fields. And as I mentioned, the electric field is irrotational because of this. So the way we defined a potential for electrostatics was by exploiting this constraint equation. We defined the electric field in terms of the gradient of this thing called the electric potential, V. And we can do that because the constraint equation is automatically satisfied by doing this. And that's because the curl of the gradient of a scalar function is equal to 0 by the magic of maths. So this applies for any scalar function v. So the constraint equation is automatically satisfied if we choose the electric field as the gradient of a potential. So that's why we chose the form of the scalar potential V as the gradient electric field. And it seems magical because we start off with a scalar field and we end up with a vector field just by taking its gradient. And that's because actually there's extra information hiding behind the scenes to do with this constraint equation. Okay, so that was the situation for electrostatics, and I'll put that in brackets. Let's now look at magnetostatics. What's the equivalence situation for magnetostatics? We have again a constraint equation for the magnetic field. It's that the divergence of the magnetic field is equal to 0. So again, this is a constraint equation because it tells us that not all magnetic fields not all vector fields, can be magnetic fields. Only divergenceless vector fields can be magnetic fields. But there's an important difference between this equation and the one in electrostatics, which is that this is a single scalar constraint equation. Rather than there being 3 scalar constraint equations, as in the case of electrostatics. So this is a much weaker condition. So we cannot define the magnetic field just in terms of a scalar potential, like we did for electrostatics. There's not enough constraint, if you like, to make that big leap. But instead what we can do is define a vector potential. And we call this A vector. And it's a field in the sense that it exists everywhere in space. So it's a vector of R vector. And we define the vector potential A such that the magnetic field is given by the curl of this thing, A. And this automatically satisfies the constraint equation, because if we want to take the divergence of the magnetic field, which we know to be equal to 0, that would be equal to the divergence of the curl of the vector potential. And this is equal to 0 automatically, again by the power of mathematics, because the divergence of the curl is equal to 0 for any vector field. And so again, we're able to incorporate the constraint equation into our definition and have it be satisfied automatically. So, in electrostatics, we often say that we have an electric potential. In magnetostatics, we often say that we have a magnetic vector potential. However, I'd actually prefer not to use these terms electric and magnetic associated with these things, because if we move away from the static limits and consider dynamics, then the electric and magnetic sides of the theory become all entwined, and we can't think about them separately. And in that case, it's no longer sensible to talk about an electric potential and a magnetic vector potential. We can't separate them out in that way. So better, and from now on, I will call V the scalar potential and A the vector potential, and I won't refer to them as electric or magnetic. Okay, so what can we do with this? Well, earlier in a previous lecture, we started from the Biot-Savart law and showed that it can be written in the following way. We showed that the magnetic field can be written as the curl of some integral involving the three-dimensional current density integrated over some volume d tau. Just a reminder here, this script r thing here, the vector is r minus r primed. So r is the point in space where we're evaluating the magnetic field B, and r primed is the point that we're integrating over. So r is the field point, r primed is the source point. This script r is the separation space between them, and what we see downstairs in this integral is the magnitude of script r, which is just the modulus of that vector. Okay, so importantly, because we've written the magnetic field as the curl of something, and because we've defined the vector potential as the curl of A, we can just read off that the vector potential A is equal to this thing. Which is very neat. So from this equation, what we can see is that typically the direction of the vector potential is in the same direction as the current. Now, this would be strictly true if it was just a 1D wire, because all of the current would be going in the same direction down the wire. And so when we do the integral over the volume, all of the current is just flowing in the same direction. In an arbitrary and generalized situation, there might be different bits of charge moving in different directions, and then we'd have to think of averaging all of that in this particular way in order to get the vector potential. But broadly speaking, the direction of the vector potential is the direction of the current. So again, this is a nice simplification because we don't have to faff around with taking cross products or divergences or curls and all of this. We just have a nice simple expression for the vector potential in terms of the current in a kind of more direct way. So this is already a kind of quite a nice formulation. If we were to look at the 1D version of this, this is very simply obtained by taking the current density in 3D, called J, and just writing this as some delta functions times a 1D charge density, the current density along a wire I. And if you do that, the integral in 3D collapses to an integral along a length in 1D or along a particular path. And then we have something very simple, which is just the integral along the line that we're interested in, the wire, if you like. Similarly, in 2D, the vector potential, again, can be just written in terms of the integral over an area, this time, of the current density in 2D K. Again, now integrated over the area. Okay, so that's pretty straightforward. Now I want to talk about something called a gauge transformation, which is rather interesting for the case of the vector potential. I already talked a little bit about this in the context of the scalar potential, and so let me just recap that for the electric side. So we define the electric field in terms of the gradient of the scalar potential, V. And then the question is the potential unique? And the answer is, of course, that it's not, because we can add any constant to the scalar potential, and that's basically equivalent to saying we can choose an arbitrary reference point for our potential. In fact, it's only potential differences that are observable. Okay, so why is that? It's because if I imagine having a different potential, V primed, which is the old potential V plus some constant, and so V is, of course, a field that exists everywhere in space, and when I say a constant, I really mean a constant in space. Everything is constant, just shifting the whole thing. Then I can look at the electric field, let's say for the primed system. This is minus the gradient of V primed, which is minus the gradient of V, minus the gradient of the constant, but of course the gradient of the constant is 0 because it's constant. And so this just reduces to minus the gradient of V, which is E. So the electric field does not depend on any constants that I add to the electric scalar potential. And the electric field is observable. Because all I have to do is multiply the electric field by the charge, and I get the force, and the force is certainly observable. It causes accelerations and so on. It doesn't affect the forces or the electric field if I add a constant to the potential. And it's, in fact, you could also look at the potential energy, and again, we know it's only potential differences that are observable. So we can choose an arbitrary reference point for our potential. And this is kind of a trivial example of a gauge invariance. And what I mean by this is that there's a certain choice we can make, which is this constant, and physical properties are invariant to that choice. And that choice we call the gauge for historical reasons. Okay, so back to gauge transformations for the vector potential. Let's see how it's similar and how it's different from the electric side. Well, we do have a big difference, which is, of course, the definition of the magnetic field in terms of the potential. It's not through the gradient of a potential, of a scalar potential, it's through the curl of a vector potential. And what I will argue is that I can add onto the vector potential something which leaves the magnetic field, and hence observables, unchanged. What is that thing? Let's consider a new vector potential A primed, which is the old vector potential A, and then I'm going to add to it the gradient of some scalar field, which I'm labeling psi here. Psi is a field in the true sense, meaning that it exists everywhere in space, but it's a scalar. So if I take this definition, then let's calculate the magnetic field in the primed system. It's equal to the curl of A primed, which is the curl of A, plus the curl of the gradient of psi, but this is equal to 0. 0 vector, to be precise. Again, just by the power of maths. The gradient, the curl of the gradient is equal to 0. So what this tells you is that I can add the gradient of any scalar field, to our vector potential, and it will leave the magnetic field unchanged, and therefore the magnetic force would be unchanged, and so on. So when we're dealing with potentials, we can choose any constants to add to the scalar potential, and the gradient of the scalar field to add to the vector potential, and this will leave physical properties unchanged. So the punchline here is we can add to our vector potential any gradient of, or I should say, the gradient of any scalar field, and it leaves the magnetic field unchanged. And again, this is another way of saying this. A fancy way of saying this is to say that there's a gauge invariance. Again, we can add on various things to our vector potential and doesn't change physical observables. So this is, if you like, a gauge freedom. Which leaves physical observables unchanged. So what's the use of this? Let me write both of them down. We have that V can go to V plus a constant, and A can go to A plus the gradient of a scalar potential psi, and it makes no difference to physical properties. So these things I've written in red here are the gauge transformations. And they leave physical properties unchanged, physical observables. So you might ask, if they leave physical observables unchanged, then what's the point? And the point is that we can choose a gauge that makes a given calculation easier, and we can also choose a gauge that reflects the symmetry of a particular problem. And this is actually very powerful, and we'll see later on that this actually really helps us a great deal in actually doing calculations, and in fact observing a more fundamental structure to the theory. Okay, so let's just see this in action with an example. What we can do is choose this scalar field psi such that the vector potential becomes divergenceless. Now, this requires a little bit of thought, but basically what it's saying is whatever divergence the original vector potential had, I just choose a scalar potential such that when I take the gradient of it, it cancels that out at every point in space. And we call this particular choice the Coulomb gauge. And it's quite a useful thing, and we'll see it in action in a moment. So the important thing to remember here is I choose this psi such that it cancels out the divergence, and then I'm left with a vector potential in this new gauge, which has no divergence. But doing all of that does not actually change the electric field and magnetic field. All the physical properties are invariant, just because of the clever way in which we do this gauge transformation. Okay, so in the Coulomb gauge, we can write down some equations. For example, we have Maxwell's equations for the curl of the magnetic field is mu naught times the current density J. This becomes, under the Coulomb gauge, the curl of, and then instead of B, we're going to write the curl of the vector potential A on the left-hand side. And then we're going to use one of the results of vector calculus to unpack this left-hand side a little bit. Because what we have here is the curl of the curl, that's one of the second derivatives. And if you remember your vector calculus, you'll remember, or at least you'll know to look up, that this curl of the curl can be written in an alternative form as the gradient of the divergence minus the Laplacian. Okay, so that's not obvious, you just have to look that one up. But of course, in Coulomb gauge, this term here is equal to 0 because the divergence of the vector potential is equal to 0 in Coulomb gauge. And so what we're left with is that the Laplacian of the vector potential is equal to minus mu naught times the current density J. So this Laplacian here is just the sum of the second derivatives, spatial derivatives. Okay, so that's extremely important. It's can be thought of as being Ampere's law, but in a differential vector potential form. And the most important thing about this equation is that, of course, it's basically like the Poisson equation in electrostatics. So in electrostatics, we had one scalar equation. However, in magnetostatics, we have three scalar equations, or one vector equation. Okay, so it's like 3 Poisson equations, if you like, for the magnetic side. Magnetic side is a bit more difficult, as you can see. So you just have to remember that this is like the Poisson equation in electrostatics, but it's a vector equation rather than just a scalar equation. So there's not quite a free lunch, if you like. Okay, so what we have is a kind of Poisson type equation, which allows us to actually do some calculations and find out what the vector potential is for certain current distributions, which is nice. And we could just use exactly the same kind of machinery that we used for the electric side of the theory when we used the Poisson equation there. Now we just do it for the vector potential in magnetostatics. And then when we have the vector potential, we can take the curl of it to find the magnetic field. And then we can use the Lorentz Force law to find the forces on particles and find the trajectories and so on and so forth. So just a little comment. If we have a vanishing current density as we go out to infinity, then the vector potential will also vanish out in infinity. And then that allows us to solve the Poisson equation for the vector potential in the same kind of way that we did for the electric potential. And what we get is this equation by using that boundary condition of the vanishing current out at infinity. This is implied by this sort of Poisson equation for the vector potential, but this is exactly Ampere's law for the vector potential that we saw previously. So this really is all nice and consistent. These equations that I've written down here, I'll put a double arrow on this, going backwards and forwards actually, indicating that they really contain the same information. So the Poisson equation for the vector potential and Ampere's law for the vector potential, they're actually the same equation, just in slightly different form. If you want a proof of this equivalence, let me just sketch it very, very quickly. Imagine putting this vector potential A on the right-hand side into the equation on the left. I want to take del squared of A that's basically going to be the Laplacian, inside the integral it's going to be the Laplacian of J divided by this script R, d tau. But the Laplacian of 1 over script R is a delta function. And so if I plug that delta function into the integral, it collapses, and I end up just with J, which is exactly what I want. Okay, so let's do a quick example. Let's look at the vector potential of a current-carrying long straight wire. Okay, let's see how this works. So first of all, it's a 1D system, and so the vector potential is parallel to the current, which is, of course, along the wire. So the direction is nice and simple. We don't have to worry about right-hand rules and curls and all of this. Okay, so what actually is the vector potential? Well, we use symmetry arguments, and we see that the vector potential is something that can only depend on the radial distance from the wire, because it's translationally invariant as we go down the wire, and there can't be any can't be any circumferential dependence because of the cylindrical symmetry. So the vector potential can only just die off as we get further away from the wire, as parameterized by the radial distance s. And we know that it goes along the wire, which I'm assuming here to be in the z direction. Okay, so let's work out, let's just sort of do this backwards and work out the magnetic field. So the magnetic field is the curl of the vector potential. Because we know the dependence of the vector potential parametrically, we know the curl of A is going to be dA by ds in the circumferential direction in cylindrical coordinates. And from our previous calculation of the magnetic field using Ampere's law, due to a 1D wire carrying a current I, we can write it like this. And that's mu naught I over 2 pi s is equal to the derivative of A with respect to s. And so we can just integrate it up to find the vector potential for a 1D current carrying wire. And it obviously just involves the log. And there's a constant of integration, which is basically a reference point for the potential, which is S naught. Okay, so there we have it. So for a 1D wire carrying a current, this is the vector potential, and again, it's along the direction of the wire. And by construction, if I take the curl of this thing, I get the magnetic field. Of course, you can get this directly from Ampere's law using A, but it's a little bit harder to do that. Okay, so in the assignment questions associated with this course, there are some examples of this, and I'll provide work solutions to those in due course. Okay, so the last topic I want to cover in this lecture on magnetostatics is the multipole expansion of the vector potential. And actually, this will follow very similar lines to the multipole expansion of the scalar potential that we looked at in a previous lecture on electrostatics. So let me just draw the basic setup, and then we can discuss what the mathematical strategy is and what the purpose of this is. So let's consider that we have some arbitrary current loop. So around this loop we have a current flowing, I. And let's say that we have some particular origin of our coordinate system. Let's call it O for origin. And what we want to know is, what is the magnetic field, or in this particular case, what is the vector potential, which we can use to find the magnetic field, at some different point. Let's call it P for a point. So this vector that goes from O to P, I'll call R. So R is precisely this vector from O to P. Good. And we want to know the vector potential at P in terms of this sort of reference origin O. And this is due to a tiny contributions to the vector potential due to current flowing around in a particular part of this circuit. Let's say we're considering a tiny bit of the path around the loop, dl primed. Okay, so that can be sort of centered on this little point here. And that vector from O to the source point we will call r primed. And just for future use, let's call the angle between r and r primed theta primed. So the vector that goes between the source point and the field point is this one, and that is this thing that we call script r. So just to remind you, the script r is r minus r primed by the usual vector addition. So what we want to do is find out the vector potential at point P due to the contribution of the current flowing around this point dl, and then we want to sum up or integrate over the whole path to find the total vector potential at point P. So to do this, we're going to use the formula that we just derived for the vector potential. So A, located, this is the vector potential A, located at a position R. This is precisely this vector OP. It's the point P with respect to the origin O. And that is given by mu naught I is the current, divided by 4 pi. And then the integral of this dl primed vector over the script R, separation between source and field points. So that's the equation. What I want to do is, instead of just blindly using this equation in its sort of raw form, in a brute force calculation, I want to do something slightly more clever. What we want to do is approximate the vector potential using a series expansion in 1 over r. And r, as you can see here, is the distance, the separation, if you like, between the source point and the field point. So therefore, if we're a long way away from the current loop, then 1 over r squared, 1 over r cubed, 1 over r to the 4, and so on, get progressively smaller and smaller and smaller. And maybe we can neglect those terms. So the idea is to have a sort of systematic way of approximating a given vector potential of any arbitrary complex current configuration. And we organize the information in a sort of clever way as a power series in 1 over r, so that subsequent terms get smaller and smaller and are less and less important. So we can sort of identify what the most important contributions are. Now, if you recall, we did something similar for the electrostatic multipole expansion of the scalar potential. And there we saw the most dominant term in the multipole expansion was the monopole term, which basically treated an arbitrary charge distribution like a point charge located at the origin. So, and then the next term is the electric dipole term, and so on and so on. And each term gets less and less important. So let's repeat that strategy here. To do that, I'm going to borrow a result that we calculated in a previous lecture. Actually, this was when we were doing the multipole expansion for the electrostatic potential. And it's this one. So let's look at 1 over script r. So this is 1 over the distance script r. Let me just remind you, if this script r is r minus r primed, then script r itself is just the modulus of this thing. And we showed previously that 1 over script r can be written as a power series in 1 over r. Not 1 over script r, but 1 over r. And how do we account for the difference between 1 over script r and 1 over r? Well, it enters like this. So we have a sum over terms. Sum over n. N starts from 0 and goes up to infinity, so this is really an infinite summation. But the information is not as bad as it looks because the information is organized in powers of 1 over r. And it involves these Legendre polynomials. And for each term in the sum, n equals 0, n equals 1, and so on, we have a different Legendre polynomial, p0, p1, p2, and so on. And the argument of the Legendre polynomial is cos theta primed. Okay, so that might look a bit horrible, but let's just plug it in to our expression for the vector potential and see what we get. So the vector potential evaluated at a field point r is equal to mu naught I over 4 pi times the sum from over n, going from n equals 0 to infinity, of 1 over r to the n plus 1, and then we have to do an integral of r primed to the power of n times Pn of cos theta primed around the loop dl primed. Okay, so this looks like it's worse rather than better, but we just do each of the terms in the sum separately and see what we get. And what do we get? Well, the first term is n equals 0, and therefore we have r primed to the 0, which is equal to 1 inside the integral, and p0 for Legendre polynomial, which is equal to 1. So that's actually extremely simple. The first term, let's take out this factor of mu naught I over 4 pi as a common factor to all terms in the sum. And then the n equals 0 term just reduces to this one. So this term that I've written here is what you get from n equals 0. Okay, then we have the next term in the series, which goes as 1 over r squared. And then we have an integral of r primed cos theta primed dl primed. And that term is the n equals 1 term. And we have higher and higher terms. And if you look up the Legendre polynomials, you can just write these out and see what they are. Okay, but let's just stop at these two terms for now and see what we get, because there's already some interesting physics coming out just from this. So let's look at this first term. There's a monopole term. Let's call it monopole vector potential. And what I mean by this is the n equals 0 term of the sum. And this is mu naught I over 4 pi r times the integral dl. Now, note that here we have the loop, the loop integral, the line integral around a loop of a vector. So this is vector displacement, the total vector displacement around a closed loop. Now, it's important that this is a vector, you see. If it wasn't a vector, it would just be the circumference of the loop, and that would be some number. But because it's a vector, we do have to do vector addition round the loop, and the total vector addition round a closed loop is equal to 0. So this is, of course, extremely interesting because it tells us there is no monopole contribution to the vector potential, and therefore there's no monopole contribution, if you like, to the magnetic field. This substantiates the idea that there are no magnetic monopoles. There are no point charges, if you like, for a magnetic field, as you have point charges for electric field. There's no such thing for the magnetic side of the theory. So this is very interesting already. And you'd learn something similar from the equation, Maxwell's equations, that the divergence of the magnetic field is equal to 0. Okay, what about the other term? We have a term, the other term I wrote down. There are infinite many of these of these multipoles, but I'm just writing down the most important ones. I can write down a dipole contribution to the total vector potential. And this one is mu naught I over 4 pi r squared, and then the integral around the loop of r primed cos theta primed dl primed. And this is not 0. It's not generally 0, okay, I should say this. It might be in a particular circumstance that this term is equal to 0, in which case the leading order contribution would come from the quadrupole. However, usually there is a finite contribution and it's the most dominant one. And this is the magnetic dipole term. It's usually the most dominant contribution because there's no magnetic monopole. But what we can see is it's already down by a factor of r on the monopole term. So we have, or what would have been the monopole term. So overall, the magnetic vector potential goes as 1 over r squared, and the quadrupole goes as 1 over r cubed, and so on and so forth. So they're actually smaller and smaller contributions. Okay, but let's have a look at this magnetic dipole such as it is. This can be written in a coordinate-free representation. So here I specified an origin, I specified this thing called theta primed, and it looks a little bit messy like this. So let's try to write this in a coordinate-free representation, and I can do that using vectors. So instead of writing this integral, which involves this cos theta primed, I'm going to write this as r hat dot r primed integrated around dl. R hat is a unit vector in the r direction, and r is the position of the field point where we're evaluating the vector potential. Now, because it's the dot product, it will give us for free this cos theta primed contribution. Okay, as a nice, another nice way of writing this thing, we can express r hat dot r primed just in terms of the cross product with the vector area now around the loop. So this is just a nice result of vector calculus, but it's nice a way of writing this thing, because what we're left with is an integral just over the loops. It's like just a geometrical factor. So this thing, the integral over this vector area, we'll just call that A. It's the vector area of the loop. And so overall, we can write that the magnetic dipole term can be written as mu naught over 4 pi r squared multiplied by m cross r hat, where this thing m, which is a vector, is the dipole moment. It's the current multiplied by this vector area. And this is something that we call the dipole moment, magnetic dipole moment. Okay, So usually the magnetic dipole term dominates in the multipole expansion, but remember that is not the exact potential. It's only the first or leading order contribution. So our actual magnetic vector potential is equal to the dipole term plus higher order corrections. And often we may feel entitled to neglect those higher order corrections, especially if we're thinking about a field point that's quite a long way away from a distribution of current. Why? Because the higher order terms are successively suppressed in powers of 1 over r. Okay, so what does this dipole potential actually look like? Well, let's write it in spherical polar coordinates. Just to get a more vivid idea. This can be written in terms of the magnitude of the magnetic dipole moment, m, no vector, sine theta over r squared in the circumferential phi hat direction. And that's just got from doing the cross products in using spherical polar coordinates. What we can do is to work out the dipole contribution to the magnetic field. And of course we do that by taking the curl of the dipole contribution to the vector potential. I won't bore you with the maths, but let me just write down the answer. Remember, if you were to do this yourself, and it might be worth having a try of it yourself, just to convince yourself you can do it. Just remember that you have to use the formulation of the curl in the correct coordinate system. So you have to look up how the curl looks in spherical polar coordinates to get this right. Okay, so anyway, that's the results when you do it and you get it right. And again, you can write this in a coordinate-free representation, which looks like so. Notice that when you take the derivative, you get another power of r downstairs. So the magnetic field is actually a 1 over r cubed dependence. So this looks a bit weird, but it's nice to write it in a coordinate-free representation using just the vectors. Okay, so what does this actually look like? Let's actually plot the pure dipole magnetic field. So what I'm going to do is really plot the magnetic field arising just from the dipole term. Not a physical situation that includes the higher order corrections, but just this leading order term. And this is what it looks like. Okay, I have to excuse my bad sketching. Okay, so you can sort of basically get the idea of what I'm trying to do. Okay, looks something like this. Okay. And we see that this is quite an interesting structure because it actually looks identical in structure to the electric field for a perfect electric dipole. So if you look at the magnetic field for a perfect magnetic dipole, and you look at the electric field for a perfect electric dipole, they actually look identical. And this is quite interesting because if you actually look at a physical dipole, so what I've drawn here is for, let's just write it, a perfect magnetic dipole. I'm really just plotting this equation that I've derived here. If I look at a physical dipole, including the higher order terms, then it looks a little bit different. I see something that, if you squint your eyes, it sort of looks the same. That's the whole point of it being an approximation. But it's not quite the same when you zoom in. Okay, so you get something that looks more like this. Okay, so you see that there are some there's some separation between these sort of poles, if you like, in the magnetic dipole, rather than them sort of separating to zero. And this is quite interesting because the physical magnetic dipole actually looks very, very different from the physical electric dipole when you zoom in. So these field configurations actually are totally different when you zoom in. But if you look at the perfect magnetic dipole, basically by zooming out, then the electric field and magnetic field due to electric dipole and magnetic dipole actually look the same. Okay, so finally I just want to do a quick example, or a couple of quick examples to make the point about how we can actually use this multipole expansion to really do some calculations and really make our life a lot easier through this approximation. So let's have a look at this obvious, simplest example of a magnetic dipole due to a circular current loop. How does it work? Well, let's always start by drawing a sketch. Let's imagine we have a current loop here. This is meant to be a circle, drawn in perspective, such as it is. And here I have my z-axis. And let's say the current loop is of radius r. Okay, that's the setup. What's the magnetic dipole moment of this thing? It's extremely simple. The magnetic dipole moment m is a vector. It's a vectored quantity, which is the current, which is I, we're given that, times the vector area, which is the integral of dA. The area of this loop is simple because it's a circle. We've just got to be a bit careful because it's a vector area, and as usual with the vector area, the vector is something that points perpendicular at each point to the surface. And so in this particular case, it's very simple. It's pi r squared times I, and then the vector is the one that points perpendicular to the surface, which is in the z-hat direction. So if we're looking a long way away from this current loop, we'll see a magnetic field that is approximately given by the dipole term of the expansion. And when I say far away, we've always got to be careful. We're scientists, so we should be precise. So when I say far away, I have to think about a dimensionless quantity that is large. And the only thing I can think of is a distance r away that's large in comparison to the internal dimensions of this object, meaning the radius of the current loop. I can't say far away unless I say with respect to what is it far away. I could say it's far away, meaning it's greater than 1, but what units am I using? So the units have to be the units of the internal dimensions of this thing. So when we're far away, which means R much greater than big R, to be precise, then the magnetic field is to a good approximation the dipole term of the magnetic field. And we just worked out what that was in terms of the magnetic dipole, and we've just worked out the magnetic dipole for this configuration, and so we're there. It's, in this case, mu naught I r squared over 4 r cubed, the pi's cancel, 2 cos theta r hat plus sine theta of theta hat. So we just borrowed the result from previously. Okay, very nice. As another quick example, let's think about a spinning charged ring. Now, if we have a ring with some charge on it and it's in motion, the moving charges constitute a current. So if we have a ring that's spinning, that's like a current flowing, and it's actually exactly the same configuration as the one we just did. So here we have a metal loop, wire loop, with, let's say, charge density lambda. And this thing is spinning around its axis, let's say with an angular velocity omega. So we can use all of the results from the previous example. We just have to work out what the current is. Once we know the current in this configuration, we can work out the magnetic dipole moment as above. And then once we know the magnetic dipole moment, we can just plug it in and find the magnetic field. So all we need to do really is find the current. What is the current? It is the rate of change of the charge, meaning dq by dt. It is this in a 1D configuration anyway. And this is 2 pi r lambda over 2 pi over omega. Okay, where did I get that? So on the top there, I wrote dq. What is the total amount of charge in the ring? It's the circumference of the ring, 2 pi r, times the charge density per unit length, which is 2 pi r times lambda. So that's the total charge on the ring. And the total charge of the ring goes round one full cycle in one sort of time period, one's period of the oscillation. So what's the period of the oscillation if the angular velocity is omega? It's 2 pi over omega. That's the time period. So I'm writing delta q over delta t, the total amount of charge that cycles round in one time period. There you go. And a lot of it cancels, and I end up with omega r lambda. Good, so that's the current. And then this tells us that magnetic dipole moment m is just pi r cubed omega lambda times, it's a vectored quantity, so we multiply this magnitude by the direction which is perpendicular to the plane of the loop, which is, in this case, z hat. And again, with that, we can plug it into our expression for the magnetic field. Okay, so that's the end of this lecture. We talked about several things. We talked about Amperes Law. We talked about concepts to do with the vector potential. And we talked about the multipole expansion of the vector potential. Okay, I hope you found this lecture useful, and I hope you join me next time where we'll look at magnetic fields in materials.